In this video, we are going to finally define the central object that is going to be our focus of study for the rest of this course. This is the notion of a differential form on a manifold. In short, a differential form assigns to each point a alternating K form defined on the vector space, which is the tangent space at that point. So to make this precise will involve some technicalities. So we will take a very pedestrian approach. The clean and elegant way to do this definition is via what is known as sections of a vector bundle. The vector bundle in question would be the vector bundle of the kth exterior bundle. We are not going to go through such advanced tools, but rather we will give a very straightforward definition. So to make this definition work, we will first define a special basis for the tangent space. So in some sense, this basis is a smoothly varying basis. So it's going to be very useful when we have to define smoothness of forms. So definition, this is the definition of frame field. So what we are going to do is we are going to take a CP manifold of dimension D. So let M be a CP manifold of dimension D. Let phi from U to M be a parametrization where of course U is subset of RD is open and phi has all the properties needed and so on and so forth. Now the frame field on phi of U defined by phi is given by the D maps E1, E2, ED. These are all maps from phi of U to Rn. How are these maps defined? Well, E1 at a point P is just given by you first go back to U via phi inverse. So you take phi inverse of P. And then what you do is you differentiate at this point. So you differentiate phi at this point, phi inverse P. This would give a linear map. If you recall, the image of this linear map is nothing but the tangent space of the manifold M at the point P. And so let me just make the left hand side EI. This is just acted on EI. Okay. So if you observe carefully, this E1 of P ED of P are all elements of the tangent space to P, tangent space to M at the point P. Okay, and of course here E1 to ED is the standard basis of RD. Is the standard basis of RD. And I must mention M is contained in Rn. That's why this map is mapping into Rn. Okay, so what is happening? Well, a picture in this scenario is really going to be worth 1,000 words. So let's draw a picture. We have some manifold M. We are focusing at a point P. We have this parametrization which makes things Euclidean. So this is U. This is phi of U. So frame field is supposed to be D vectors that together span the tangent space of the manifold at the point P. How are these D vectors determined? Well, you go from P back to Euclidean space via phi inverse. Okay, phi inverse P will give you a point. Let's say it's this one. Then what you do is you look at the standard basis here, E1, E2, E3. Then push forward that standard basis via the derivative map. This will be D phi at phi inverse P. That will give you D vectors that are in the tangent space at the point P. Of course, here I have drawn 4, therefore I must draw 4 in the Euclidean setting also, even though I don't know how to draw 4-dimensional space on 2-dimensional paper. I don't even know how to draw a 2-dimensional figure properly on a 2-dimensional paper. So forget about the 4-dimensional case. But in any case, what we do is you push forward these vectors e1, e2, dot dot dot, e1, e2, e3, e4, so on. You push forward and you will get d vectors in the tangent space. Together they will span the tangent space. So the nice thing about the frame field is it's sort of smoothly varying because all the maps involved are smooth. This phi inverse and phi and everything. As you change the point, the vectors do not change drastically on the manifold. So this frame field is going to help us define smoothness of a general differential form. So we now come to the definition of the differential K forms on a manifold. So definition, let M be a d-dimensional smooth manifold. So let me make a remark regarding the smooth manifold. I'll do it verbally. I'm not going to write this down. Henceforth, for the rest of this course, we are only interested in smooth manifolds and smooth forms defined on manifolds. These are the most this is the most useful setting for manifold theory. For some purposes, you may need to study CK manifolds, more specifically K equal to 1 or 2, C1 or C2 manifolds. But in this course, and indeed in most courses on Riemannian geometry, they focus only on the C infinity case. So we will also focus only on the C infinity case. Henceforth, I will just write smooth manifold to mean C infinity smooth manifold. And whenever I use the word differential form or just K form or just plain form, I mean it's a smooth K form, smooth in the sense of C infinity smooth. Okay, so let M be a d-dimensional smooth manifold. We are going to define this complicated space, which I'm going to call alt Km. This is an ad hoc definition that I'm doing because I do not want to introduce vector bundles. So this is going to be defined to be a comma eta, where a is a point in M, and eta is a K form, on the tangent space. So it's alt K TAM. Okay, so I'm going to look at all pairs a comma eta where a comes from the manifold and eta is the K form defined on the tangent space TAM. Okay, now remember, I have repeatedly emphasized that a differential form assigns to each point of the manifold a alternating K form that lives and feeds on the tangent space. So the definition should not be surprising. A K form on M is a map omega from M to alt Km. That's it. At each point, it assigns a alternating K form defined on the tangent space at A of M. If I add the notion of bundles, I would have just I could have made some simplifications. I could have just said it's a section of the bundle, but I'm not going to do that now. Okay, now let's define smoothness of this form. Let phi from U to M be a local parametrization and E1 dot 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 ED be the associated frame field. This comes from the previous definition. Then you can write omega of P as summation I running through IDK AI of P EI star of P. For the definition of what this EI star of P is, refer back to the previous videos. These are some basis forms that I had defined when we studied this space of alternating K forms on a vector space. So since these E1 dot 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 ED form a basis, I can use that to define a basis of k-forms, and any k-form at a point at the tangent space TPM can be expressed in terms of these basis vectors. So what will happen is at each point P, I can obtain an expression for the form in terms of this EI star of P. Now what will happen is this AIs will be functions. They will be functions, they will change from point to point. Of course, EIs also change from point to point, therefore EI star also change from point to point. Okay. We say omega is smooth if the functions AI from phi of u to R are smooth. Okay. So or if you prefer, you can also say that AI composed with phi from u to R is smooth. Both are equivalent. If you prefer to directly go to Euclidean space and define smoothness using the chart, not the chart, using the parametrization, you can directly say AI composed with phi is smooth. Now this should be true irrespective of the parametrization. That means no matter what parametrization at whatever point in the manifold I choose, when I write down the form in terms of the frame field obtained from that parametrization, I must always end up with smooth functions. Then I say that the K form is smooth. Okay. Now the collection of K forms on M will be denoted omega k m, and it's an easy exercise to show that this omega k m is a vector space, and that fact will be repeatedly used because we are going to define lots of operators on this vector space. Okay, now a number of remarks are in order. So let's make them. Remark number 1. We have made a tacit abuse of notation. Omega p is actually a pair. It's p comma something, right? That's the way we defined it. It's p comma some form, right? But if you look at the definition, I say omega p can be written as this. That's because I am harmlessly neglecting the first coordinate, which is going to be p. That's an abuse of notation that we will repeatedly engage in. So is actually a pair, but we will ignore. But we will abuse notation and just identify omega p with the second coordinate, which is actually the thing that matters, with the second coordinate. This is a harmless abuse of notation. Okay. Now the second remark is going to be more interesting. The definition is pointwise. The definition of a form is pointwise. That means at each point you assign to it a alternating k form, right? So is pointwise. So we can do pointwise operations. So we can add and multiply by scalar. In fact, you must have checked all this when you checked that the space of k forms omega k m is actually a vector space. Multiply a form by a scalar, etc. You can do these pointwise operations, but more importantly, you can take wedge product. You can take wedge product of two forms. Wedge product of two forms. These are not two hyphen forms. It means take a pair of forms. That's what two here means. Of two forms on a manifold. You just do it pointwise. You know already how to take the wedge product of a form on a vector space, you just do it pointwise now. Okay. Now third remark is important. These coordinates AI are not unique. They obviously depend on the chart. That's why you have to check for every single chart that the functions AI are smooth. Okay. And the fourth remark is rather trivial but needs to be made. Zero forms are just functions. Think about why this is so. Think about why zero forms are just functions. Yeah, so these are some of the remarks that I wanted to make. I want to give you an exercise also. Exercise. Let f from m to r be a smooth function that is a zero form. What is f wedge omega where omega is a k form? How will you take the wedge product of a function and a k form? The answer is going to be the most obviously guessable thing, and I'm not going to spoil the surprise. Okay, now in the next video we are going to analyze these forms further, but before we do that, we are in a bit of a quandary. If somebody hands you a smooth form on a platter, there is no easy way to check in fact that it's a smooth form. You will have to check for every single parameterization that the associated coordinate functions are going to be smooth. There will be uncountably many local parameterizations of a manifold, so it's an impossible task unless you happen to have uncountable time on your hands. But it turns out that you need to check only for a collection of parameterizations whose images cover the entire manifold. You needn't check for all possible local parameterizations. There's no necessity to check for all possible local parameterizations. So we are going to analyze that in the next video. So for that we'll have to introduce pullbacks and do analysis of pullbacks on Euclidean space and so on. So a lot of fun in the next video. This is a course on real analysis, and you have just watched the video on forms on a manifold.